Hello there, my name is Nick Babin, and I'm an assistant professor at Cal Poly State University in San Luis Obispo. And in this short video, I will be sharing with you a procedure for taking publicly available climate change data, or climate data, both historical and projected data, from this website, the caladapt.org website, and creating a narrative projection or scenario for a particular locale. And one of the many things that this website does is it projects future climate at different scales. So you can project anywhere from the scale of the watershed or the county. And then for our purposes, for agricultural purposes, very interesting that we can project down now to a 6 kilometer by 6 kilometer resolution grid. And so this gives us a little bit, I would say, more useful data and usable data for agricultural adaptation. Given all the microclimates and topographical variation, we're able to get a little more fine-scaled projection. So I'll share with you one particular procedure. There is a wealth of data on this website. We're just going to scratch the surface. So first off, starting at the website, it's caladapt.org, and different ways to go about accessing the tools. I think the easiest way, click on this Tools tab in the top right, and then you'll see the assortment of different projection tools. And it includes information on future projections as well as past observed values for these different indicators. So you have your annual averages, extreme precipitation and heat events, wildfire, drought, all these different things. So you really have a wealth of resources here at your disposal. And what I would say is play around with it, but you can also, after playing around with it, come down to a number of indicators that you really want to look at so that you're not overwhelmed. And so what I'll do now is I'll share with you, and this will also be available, a template that we've created of 5 or 6 different projections that we found useful for sharing with agriculturalists around adaptation planning for their particular farm or ranch. And so you can see this is templated out. We have like kind of gaps here for the values so that you can fill them right in. And a lot of this is modular. The time ranges you can play around with, and when we look at thresholds in these later ones, you can play around with the temperatures. But big ones are annual maximum temperature, and this is the observed, 1961 to 90. We choose that time range because that's before the imprint of human-induced climate change kind of kicked in. You can also change it from 1961 to present or 1990 to near present. So then you get the annual maximum temperature and the range over those years, and then 2 projections is what we're going to create for each one of these. One a short term, 2021 to 2040, and one more medium term, 2050 to 2070. You can also go as far as 2099 and any range in between there. These are just the ones we've chosen. Again, it's modular, and you'll see that when we bump into the tool here in just a second. Annual minimum temperature, the same, the observed, and then projection in the near term and more medium term. Historic average rainfall over a particular time frame, and then over the next decade. This one's a little different. What are we looking like in the next decade? And then mid-century. And then heat. Average days per year above 90, and then projected. Average days per year above 95, and then projected. As you'll see, you could create these thresholds higher or lower if you want. This is just what we decided to use. And then heat waves, the number of times per year when you had at least 4 days in a row of a particular temperature. We chose 90 degrees. And then minimum temperatures, average number of nights where minimum temperatures don't fall below a particular threshold. That's important for many of our crops, perennial crops, especially in the state. And then burned area, annual average area of burn, and then the projected. And what you'll see here in the red is what we've created is a way of comparing the projected for each indicator back to the baseline. So up here it's the increase in temperature or decrease, although really we don't see too many decreases. And then here it's the number of inches and so on. All right, so a lot of information there. You could use more or less or create your own template. This is just hopefully to make things a little simpler. Let's go to the tool. So we're going to start with annual averages. Click on annual averages, and our first task is to pick our locale. So you have your location here with a map. Press change. It defaults to Sacramento, and there's a couple different ways. You can just put in your address, and it'll bring up the 6 kilometer by 6 kilometer grid that you live in. You could also just put in a zip code. You could also explore if you don't know the address or you're not working with a particular address or zip code, but you're kind of just looking at features on the landscape. You can explore, say, west from Sacramento here. You can also click on this satellite mode so you can see topography. You can zoom in there and kind of try to find the locale and the grid that you're particularly interested in, and then just click on it, and that becomes the grid cell that's used for the projection. So here we'll just use this one. We'll use two grid cells to the left of the West Sacramento, and that'll be important to remember where you're at. If you have an address, it's no problem, but if you're clicking like this, you got to remember it because you might need to reset the location. So you can just go update chart, and then you get to pick your scenario. So it defaults to a rather optimistic scenario where our emissions peak around 2040 and then decline. We're currently on this trajectory, the RCP 8.5, and that's where emissions continue to rise through 2050 and then plateau by the end of the century. So we'll go with that one. Then you get to pick your model, and it's beyond the scope of this short video to tell you to go over the models and try to justify one over the other. But generally, we think we've seen that averaging out the models, the run of like 6 to 8 or however many models you want to put in your universe, is the best. It leads to the most accurate projections, both backcasted projections when we check the validation of the models or future. So what I would suggest, or what we use, is we unclick all of the models except for the CAN ESM2 average, an average model. All right, and now you have it. So here is your observed historical maximum temp. It's between 61 and 1990. Remember, that was our first indicator there. The average is 74.3. The minimum, meaning the coolest year, the average maximum temperature between 61 and 90, average this, and then the warmest year. Then you can see 2070 and 2099. Remember, that's not actually the time frame that we are concerned with. We want to look at 2000, you can see how it's modular here, 2021 to 2040 was the frame we used in the template. And you can see the average increases to 79, minimum 76.6, 80.7. And so then you would say from this, you had an average increase of, what is that, like 4.7 degrees Fahrenheit. So if you go back to this, that would be our observed, and then the 2021 to 2040, and then the 4.7 degrees would go there. You fill all those in, and then you run it, and then you just come back to it and run it for 25 to 2070. Average minimum and historical average rainfall, let's look at those next. So again, if you wanted to change it to 2050 to 2070, it's right here, right? Just click these along. Average minimum, very similar. You just come up here to maximum temperature, click on minimum temperature, and here you go. Average minimums, historical observed. Again, that you can switch around, but that tends to be a good range to look at what our historical climate was. And then you can see the changes at 2050 to 2070. The modeled historical, that's what the model that we're using, this CAN SM2 average, would have back projected for the number, for the average minimum. And what that can tell you, we don't usually use it, but what it can tell you is how accurate this model is. How well does it do at representing the past? It's doing all right. I've seen more precise, more accurate actually. But pretty within a reasonable range, but we don't use that for this purposes. We want to use the observed. Another thing that can be neat to do is to check the observed historical with what your perception of the observed historical was. Granted, this isn't the observed historical the last 20 years, right? This is 61 to 90, and you might not have reference for that, but you can go up to 2005, so you could maybe do your observed historical 2000 to 2005 as your observed historical. All right, so that's a minimum. Let's go into precip. Let's look this back to 1961 to 1990, kind of our range that we've been using. And you see the average 17.9. And look at this. You see the modeled projection for this part of the Sacramento Valley. Wow, by a significant increase. But you can also look at the minimum and maximum years. We're going to have a projection of 1 year in there at least of getting 48 inches and a year of getting 7. See, that's similar lower bound, but upper bound is much higher. So several large rain event years. So here you go. You can fill that in here. Again, we did, oh yeah, that's right. For this projection, I suggest doing 2021 to 2030. So let's do that. Let's head back to it. Model projection over the next decade. And this is just because in terms of projecting future climate, our temperature projections are fairly good, especially when compared to, they've proven to be fairly accurate when we do backcasting or model validation. Look at what the models 20 years ago projected and what we actually experienced. Precipitation a little less so. So far out precipitation modeling is exploratory at best. But here, if we look at the next decade, fairly similar range of precip in this locale. Again, that's the beauty of the tools. You can this is going to range quite a bit across the state. Let's do heat. So here you have heat waves, and so we have average days per year above 90, above 95, and then heat wave of 4 days in a row of plus temperatures. So here we're going to actually switch our tools. So we'll go back to tools, and we'll go to extreme heat. And the only issue here, this is one that you really have to pay attention to, is now you've defaulted back to the models and the projection locale is defaulted back to the original one. So we have to go, in our case, we were going 2 over from West Sacramento. So reset it there, update the chart. Then we also have to go back to RCP 8.5 if that's the projection we're interested in, and then kind of get down to our average or smoothed, our average model. All right, so if we wanted to do days above, let's do days above 100 for this case. So it automatically calculates a 98th percentile. You can change that, user defined, go put 100. And as you can see, 1961 to 1990, observed historical, 15 days per year above 100. By the end of century, this model is projecting 87 days per year above 100. But let's just look over the next, over the kind of the near term. We're looking at 48 days. So above historical, yes, by 33 days. So then you'd come in here, projected days. We did above 100, and the number of days. In our case, what did we say? 33 days plus an addition, and then you can calculate for 2050 to 2070. Then you can do it for however many different categories of heat you want to look at in terms of upper threshold or lower threshold, really. Then let's look at the heat wave pool. So here it is heat wave frequency. So here we have, again, we've defined it as 100, and we've defined it as a 4-day heat wave. You could change this. So historically, there were 1.6 times per year. So over that 30-year time span, it averaged 1.6 times per year. Did you have 4 days in a row above 100? By the end of the century, it's expected to happen on average 18 times per year. And over the next near-term projection, 2021 to 2040, again, 8.5 times per year. So that's an increase of like 4 times at least, more than 4 times. 4 times plus the frequency of these events. And so that's kind of how we've captured it here. 4 times the frequency of events, that's in red, but you can fill in the template here. And again, this part is modular, right? You can change this. In fact, for that projection, we used 100. You can change that to whatever you want. All right, let's go for average nights per year of minimum temperature. So warm nights. Warm nights, again, this is the 98th percentile of days. We could change this, user defined, say to something like 55. This might be more relevant agriculturally. And here we have, there were 13 nights per year on average between 61 and 90 where temperatures did not fall below 55 degrees. And in the near term, we're looking at 30 nights per year. If we go to the end of century, it's pretty striking. We're looking at 3 to 4 times the occurrence of days per year where it doesn't where the temperature doesn't fall below 55 at night. And then burn area. Final one we'll look at. Here we have to go back out of tools and go to wildfire. And here you have to change it to 8.5. You could mess with the population growth scenario, which is a input value into this model, but just leave it to get a general idea at the center. And then we want to search by here. It's a different search tool. Let's just put in Sacramento, and then remember we were kind of 2 over here. You can fine tune that. And so this is what you get. Average of 9, between 61 and 90 hectares burning, with a minimum of 1, maximum of 25. And by 2035 to 2064, you have this range and average. You can change all of this. This is all modular. You could change the custom year, end of century for the fire. So the fire tool uses a little bit different interface, but the same kind of functionality is available, and that you're able to really tailor it. So hopefully that gives you an idea to begin exploring this tool, and maybe even utilizing the provided template, as a way to begin determining or generating a projection for your particular locale. If you have any questions about the tool, I'd be happy to answer how our labs utilized it. It's nbabin, B-A-B-I-N, @calpoly.edu if you have any questions. Thank you very much.